Now that we have a solid foundation in probability, we want to take things to the next level and sort of start to put together a lot of the information that we've learned throughout this course. So in this video, we're going to look at what a random variable is and what the expected value of that random variable is. So we're already very familiar with values like mean and standard deviation. And so what we want to do is to look at a situation and determine how data should behave given the information in that situation. So we want to know what is being expected, and in a later section we're going to look at what is expected versus what we actually sampled. So it's going to put everything together. That's the last couple weeks of this course. So before we start learning what the expected value of a random variable is, obviously it's important to understand what is a random variable. Why do we have them? So a random variable is just a capital letter that we use to represent a real life situation. So for instance, we have been looking at probability of, say, flipping a coin or rolling a die. And so if I were talking about a random variable x, I'm going to say x represents flipping a coin. And so what are the outcomes that x could be? So x could be heads and x could be tails. And so the big X just represents this is what a situation is. It's a real life situation. It is an event that is occurring. And then what we're going to do is look at all of the different outcomes in the sample space that create that event. So to this point, we've looked only at discrete random variables. Discrete meaning I can count them. All possible values can be listed. So when I was looking at flipping a coin, I could get heads or tails. When I was looking at rolling a die, I could get 1, 2, 3, 4, 5, 6. So we're going to spend a lot of our time there, but then we're going to continue and look at continuous random variables. And a continuous random variable is where I can't list all of the results. So if I said, how long does it take you to do your homework? One person might say, 20 minutes. Another person might say 31 minutes and 29 seconds. And I can't list all of those because we could go down to the 31, 29, 02 and down to the, 100th of a second. So we can't list them all, and therefore it's called continuous. So we're going to handle those in a little bit different way. But what we're looking to do right now is to come up with a probability model. And you will have a question like this on your assessment. The probability model is the list of all of the possible values and their probabilities. So if I wanted a probability model for flipping a coin, that's an easy one, then my outcomes would be heads and tails, and my probabilities would be 0.5 and 0.5. And that would be considered a probability model. And again, this is a model because it's what we expect to have based on the probabilities of 0.5 and 0.5. So what we're going to work on now is once you have that model, so first find the model, and then once you have that model, how do we determine what value we can expect? So let's take a look at a have a heart game, and I'm asking, hey, would this be worthwhile for you to play my game? So if it costs $5 to play, and from a deck of cards, I'm going to basically fan out a deck of cards, and you're going to randomly draw a card. And if you draw the card and it's an ace of hearts, I'm going to give you $100. But keep in mind that it has already cost you $5 to play, so you're actually winning $95. And then any other ace, you get $10. So you're actually winning $5 because you've paid me $5 to play. Any other heart, you get $5. and so that means you're actually not winning anything. And any other card, which it doesn't say that because of course if I'm trying to sell you this game, then I wouldn't tell you what the bad thing is. Any other card, you're giving me your $5. Okay, and I'm asking, is this a good game to play? Well, how do I determine that? The way I can determine this is first to create a probability model. Now my probability model looks like the result, which is sometimes the same as the outcome, but in this case I'm going to do another result column, and then outcome, and then probability. So that's what a probability model will look like. So in this case, my result will be the ace of hearts. The outcome is that I won $95. And what is the probability that I get an ace of hearts? Well, there is only one ace of hearts out of 52 cards. Next, any other ace, if you play cards at all. So I'm going to put other ace. And if you play cards at all, you know that there's 4 of each value in the deck. So there's 4 aces. And therefore, there are 3 left out of 52. And again, my outcome there is that I won $5 if I got any of those 3 other aces. Then we have any other heart. Well, there are 13 of each suit, and I've already used the ace of hearts up here. So now it's 12 out of 52 would be other heart. And what was my outcome? That I broke even. And then any other card, so I'm going to put other card, the outcome is that I've lost $5. And how many cards do I lose with? Well, if I have 12, 13, 14, 15, 16 out of 52 that I won with, then I'm just going to take 52 minus 16 and say that I lose with 36 cards out of 52. So again, if I'm looking at the probabilities, those add to 1. They have to. And this is what is considered your probability model. Now we haven't talked about what to do with that yet, but just so you understand, this would be the actual probability model. Now the question is this a good game to play? So let's take a look at how we determine that. So to determine if this is a good game to play, we're going to find the expected value. And the expected value is actually going to end up being the mean of our probability model. So expected value is essentially the long run average. So we've talked about the long run theoretical average. And the way that we determine it, and again, notice all of this stuff here that is not in blue is the same probability model that I just wrote down. So I've got the $95 and the 1 over 52, the $5, 3 out of 52, the $0, 12 out of 52, or I reduced to 3 out of 13, but it's not necessary to reduce. And then the losing $5 for everything else. Now what I'm going to do to find the expected value, or mean, and again mean is mu, is essentially I'm going to take the sum of all x's times the probability of x's. Now what does that mean? That means take each outcome, multiply the outcome by the probability, and add all of those together. So here I've taken 95 times 1 over 52, and that gave me 1.827. So I wrote that number here. Then I took 5 times 3 over 52, which gave me 0.288, and I wrote that number here. And then 0 times really anything is 0, so I wrote that number here. And then negative 5 times this fraction, either one, either before or after I reduce, and I get negative 3.426. And what I want to do then is I want to add up all of those numbers, and I get negative 135. So what does that mean exactly? That means each and every time I play the game, I'm expecting to lose $1.35. Now, I have a lot of students who say, well, if I took 5 minus 135, I'm actually winning money each time. But that is not the case. Remember, I already took into account that you paid $5. That's why this is 95 instead of 100. So this is saying every time I play, I lose $1.35. So is that okay to say that I lose $1.35? Yes, it is. It doesn't mean that I can play one time and lose $1.35 because, as we know, I'm either winning 95 or 5 or losing 5 or not doing anything. So I'm never going to actually lose $1.35. This is the long run average. So that means if I keep playing and playing and playing and playing, each time I'll lose an average of $1.35. So in the real world, who thrives off of this concept? Obviously, the casinos do, because they're saying, yes, you might be that lucky person who walks into that casino and you win that $95, but in the long run, the casino's making $1.35 every time somebody plays that game. So again, the formula is right here, and that says to find the center, which is the mean, mu, which is the expected value of our random variable, we take the summation, sum means add them up, of all of the outcomes times their probabilities.